Hey everyone, welcome back. In this video, I'm going to walk you through the project that I did as a part of my internship at Expose's Data Labs. Now, the project is about diabetes prediction, and as you know, it is a classification machine learning problem. And yeah, I'm going to walk you through what I did. And one more thing, this the project file will be available as a part of Kaggle notebook. I'll mention the link in the description box below. So feel free to upvote it if you like it. So without any further ado, let's start. And yeah, I'm going to give you an overview of machine learning algorithms that I've used. I'm not going to extend in detail because it will take a lot of time. This video will be, I guess, 10-15 hours long. I don't want to make such a long video. And if you want to learn more about those algorithms, I'll of course mention the links where I have learned these algorithms so that you can learn them at your own pace. So first part is the importing the libraries. Matplotlib and Seaborn is used for data visualization, NumPy for numerical computing, and Pandas for data analysis. Right, you might be knowing this. Then I import the dataset, and this dataset is basically the PMI Indian diabetes dataset. Let me show you. So this is a dataset that I've used, PMI Indian diabetes dataset. This is a very famous diabetes dataset. It is basically a dataset about all the patients being females. All right. So that's why it has a pregnancy column. I'll come to all the columns in a bit. I'm not going. All right. So I've imported the dataset. Then time for exploratory data analysis. Now, what is exploratory data analysis? You can say I'm trying to see what my data is trying to tell me. What all features are related. What all columns affect my outcome most. And that's all we're trying to see. Now, first step, we basically check all first 5 rows. That's just a general way of doing it. Get a sense of what are the values and what's present in the dataset. So I check first 5 rows. Then I basically check how many rows and columns are present. It turns out that there are 768 entries and 9 columns, or 9 features, if you will. And then the standard way is to just plot a correlation matrix. Now, what is a correlation? Correlation is basically a correlation between two features. Basically, says how strongly related they are. Now, what I mean by that is the correlation generally correlation lies between -1 to 1, and the value closer to -1 and 1 indicates there is a strong correlation between them. Now, what does it mean? Now, if it's a closer to +1, it means that as the one feature increases, another feature also increases. Now, the best example, let me just say the outcome, and the correlation of outcome with glucose is highest. It's 0.47. You can see here, right? This is outcome, and this is glucose. So what does it mean? It's a positive correlation, and it is 0.5, right? It's closer to 1. So what does it mean is as glucose levels increases in a patient, the outcome also increases. Basically, the chance of person diabetic increases. That's what it means here, because outcome can either be 0 or 1. All right. And let's just take another example. The BMI and outcome, there is a correlation of 0.29. It means there is not as much strong relation as glucose and outcome, but still, when BMI increases, there's somewhat outcome increases, or somewhat a person being diabetic, the chance increases. All right. And then we check for null values if they are present, and it turns out there are no null values here. Then we get a sense of what are the data types of the columns. So that's what I've done here. It turns out we have numerical data everywhere around. Then we are generating the summary statistics. Now, what are the summary statistics? Basically, some important statistics that will give you a sense of the data again. Now, for example, for pregnancies, there are 768 rows that you already see. The mean, that is the average pregnancy of a person, there is a 3.8. The standard deviation, the mean, and these are the quartiles, right? Now, what is a quartile? You might be knowing it. For example, this 50% is basically the value which is greater than the 50% of the values in this feature. Alright, so by observing, you can see that for glucose, blood pressure, skin thickness, insulin, and BMI, the minimum values are zeros. Now, this is actually not possible, of course, provided the person is not dead. If the person is dead, then this might be possible, but I don't think that's the case here. So this is not possible, right? So it seems like the null values are present in terms of these zeros. So we need to take care about them, right? So before I take care of this thing, so let me see what are those null values. So first time what I did is replaced all of them with this np.nan, which is null. Now I did that because it will make easy for me to visualize them using this isNA function that I used above. Alright, so that's the only reason I replaced with nan. And here I have visualized them. Now it seems like there are more than half of the entries in insulin to be 0. Alright, so if I replace them with some value, then it will have effect. Now, what will happen after imputation? So what happens is we replace the null values with a mean or median in case of numerical or continuous data. For categorical data, we use mode. Now, it turns out that as more than half of the insulin columns have 0 or null values, the insulin's mean will increase. Alright, so then I'll simply replace all of the null values with the mean. Alright, so this is what's happened, and insulin's mean has increased. It's 155, and earlier it was around 79, so it is almost doubled. And then there is a beautiful function in Seaborn, there's pair plot. It basically helps you visualize the relationship between each and every variable. Now the correlation part that I was talking, you can see here, just focus on this glucose part, and this green dots basically represent diabetic persons, and this blue represents a non-diabetic person. Now you can see here as glucose increases, more and more green dots are formed. You can see here, you can observe here, right? So what this says is the positive correlation. This explains the positive correlation between glucose and the person being diabetic. Alright, it's not like it will show you there. You can see many more relations. For example, let's just say the relation between skin thickness and this BMI is also linear. So as skin thickness increases, BMI also increases. So it just helps you. There's a pair plot basically helps you get insights about how your features are related to each other. For example, for pregnancy and pregnancies, if both the feature X and Y axis are same, it basically gives you a histogram. Now, histogram you might be knowing, it just gives the distribution of data. And then I check how many outcomes, how many number of outcomes are present. For example, out of 768, 500 of those are non-diabetic patients and 268 are diabetic patients. Alright, so here I have stopped the exploratory data analysis part. In real sense, you can actually go on to exploratory data analysis. People actually make entire projects on exploratory data analysis. Alright, but I stopped it here because the focus was on building machine learning models. Alright, so before we build the machine learning model, the most important part is data pre-processing. Now, what is data pre-processing? In simple words, it's preparing the data so that my model will work perfectly. It should not have any trouble working on the data. That's what I'm saying. Alright, so that is a simple way. The first step, extracting the input features. Now, this X basically contains the first 8 columns, if I'm not wrong. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so these are all inputs, right? So in technical jargon, these are called my independent variables. This outcome is what you call an dependent variable. And then I split it the data set into training and test set. Now, the idea is what we do is we don't train the model on the entire data set. Why? Because we want to actually test its accuracy, right? So what we do is that this train set acts like our data on which the model learns. And the testing set is like a new data that we feed to the model and we see how well it performs. So that's the idea of splitting. So I splitted it, and we split it in a way that 20%, this test set 0.2, 20% of data is in test size. So 154 samples are in test set, and how many? 614 samples are in training set. Alright. And then comes an important part. We have done we have done extraction of features, we have done splitting of data set, and now comes feature scaling. Now this is, I would say, very important thing if you want your model to perform well. So what is feature scaling is basically, why do we need first feature scaling? The reason we need feature scaling is, if you see here, let me show you the summary statistics. You can see the glucose maximum value is 199 and insulin maximum value is 846. Alright, and pregnant maximum value is 17, and the diabetes pedigree function maximum value is just 2.4. You can see this is some order of 10. Order of all the values lies between 1 and 10, and here all the values nearly goes to 1000. Now this will not, in machine learning, this will not give you a good model. Alright, some models give you, some models don't need feature scaling, but it doesn't hurt to do feature scaling. So the idea of feature scaling is there are basically various types of feature scaling. So there is standardization, there is normalization, and some different variants. But the most common way is this the standardization or z-score normalization. And we basically what we do is for every feature we fit a standard Gaussian distribution. That's the idea. That's what this guy is doing. And what it will do is you will observe that for each and every column, for each and every input, the mean will be brought down to nearly 0 because that's how Gaussian distribution works, and the standard deviation will be nearly equal to 1. Now don't think it like, okay, this minus 0. No, you can see here the E is minus 10.7. It's very close to 0 value. Alright. So now you can see the data are pretty much similar. You can see that now the maximum values are all are in order of 10, right? They all are in a range 1 to 10. You can observe that. So that's what we wanted. Alright, so the moment you all have been waiting for, finally we are going to see the classification algorithms that I have used. But before we discuss that, I just want to show you what does a classification algorithm actually do. Any classification algorithm, the idea is simply to draw something what we call a decision boundary. Now, what is a decision boundary is, in simple terms, it's a line, or more technically, it's a hyperplane that divides the different classes. As we have binary classification problem, there are only two classes, right? So the way decision boundary works is, let's just say we have this kind of data, and x1, x2 some features, and depending on x1, x2 values, some class 1 values fall here. Let's just say these are some positive values and these are some negative values. Okay, let's just assume that. Now, any classification algorithm, okay, with respect to any classification algorithm works is, they try to find a decision boundary. Now, what is the decision boundary? In simple manner, at a very simple level, it's considered as a line which divides the entire input space into two parts. And one part contains one class, another part contains another class. Now, of course, it's not like every time we'll be able to find the decision boundary, but that's the idea. We basically divide the entire input space into two parts. Now, it might happen certain times that one positive class might be here and one negative class might be here, but it's okay. We try to minimize something called as an error. Okay, and that error value depends on algorithm to algorithm. Alright, in case of decision trees, there is impurity. In case of logistic regression, there's some cost function associated with it. In case of SVM, there's something different or something like that. Okay, but that is the idea. We just aim to find a decision boundary, and it has a fancy name. It is called a hyperplane. Okay, now here it was a line. Okay, but it might not work every time that we'll have a line. Okay, it might not be the case that we'll have a line every time, right? At times we might have to fit some complex decision boundaries. At that time, let us say this is some kind of data. Okay, so here the circular decision boundary makes sense, don't you think? So all the one class lies here and one class, of course, it should be just a little bit bigger to avoid overfitting, because we don't want the decision boundary to predict is too good. It should not be too good. It should generalize well on the new data set as well. So yeah, that's the basic idea of classification algorithm. Let's move back to the Jupyter notebook and continue from the project. Alright, let's see what are various models that scikit-learn has to offer. Now, in general, to fit any scikit-learn model, what is the procedure is, you fit the model to the training set. That is, you learn from the training set and you then predict the values from the testing set. Okay, and that's what this guy does here. I'll come to this in a bit what I have written here. That's what this guy is. So any classifiers was fitted to the training set, and then predictions are made using the classifier. That's the idea. Any classification algorithm in scikit-learn works like this way. Now, to make my life easy, what I've done is I've created two functions. Now, first function basically helps me display what you call a confusion matrix. Now, what is a confusion matrix? It's just a performance metric that helps us to judge the performance of a classifier. Okay, I'll discuss in a bit. Just stay with me for a while. So this function computes the confusion matrix. It takes the whitest. So basically, these are the true values that we actually know, and it takes the predicted values and it generates something called as a confusion matrix. All right, and it shows in a way that will be very soothing to eyes. That's what this function does. And this just classifier, what it does is it takes the classifier, it fits it to the training set, computes the prediction, generates a confusion matrix, and returns an accuracy score. Now, what is this accuracy score? Accuracy score is basically the number of true prediction upon total number of predictions. It is very simple. Yeah, there is no catch there. It's a number of true predictions upon total number of predictions. Because we are giving this white test, right? So what we'll do is we'll make some predictions. That is, we'll make some predictions this by pred, and we'll give it to this display CM function. Now display CM function displays the confusion matrix and returns me that accuracy score. That's what it does. So yeah, these are two functions that will make my life easier. So I don't need to just show you again and again. I have to fit it, then I have to make predictions, then I have to get accuracy score. That's why I just made these two functions to make my life super easy. Alright, so let's start working our way through the various algorithms. Now first in our kitty is logistic regression. Now logistic regression is one of the oldest and very simplest algorithms, if you will, for binary classification. The way this logistic regression works is the function that it maps to the input looks something like this. Y cap equals to g of theta transpose x. Or let's just forget the theta transpose x, consider it like something like this. Theta 0 plus theta 1 x plus theta 2 x2 or theta 3 x or something like that. Okay, the theta transpose x means something like that. Okay, not something like that, it is exactly like that. So basically the theta transpose x weighted sum of features. That's what theta transpose x means. And we give it to the function g, and that g is what we call a sigmoid or a logistic function. And that logistic function has a beautiful property that it squishes down every real value between 0 and 1. You can see the graph of logistic curve, if you will, at the screen. Now, what does this y mean, to be honest? This y basically means, this y cap basically means the probability that y of an outcome equals to 1. In this case, the probability that a person is diabetic when input x. That's what it does. It takes the weighted sum, weighted sum of features, and give it to a sigmoid function and gives return their probability. You might ask, where are the theta derived from? There is a mathematical derivation behind that. We have a cost function associated with it, and we do some math. You might have heard the term gradient descent. That's what's used. But you just need to know this is how algorithm works. Alright. So it has fitted the data and we have made some predictions, and this is the confusion matrix. Now what is the confusion matrix? The thing you should be concerned about are these diagonals. These diagonals, the more the elements in diagonals, the good your prediction is. Now more concretely, value Cij, let's just say C00 for 0th row and 0th column, basically represents number of items or number of samples which were in group 0, that is in 0th row or ith row, and are predicted to be in jth group or this 0th column. Okay, for example, this guy will be, it will be 1 1, right? So this 28 predictions were predicted to be in first, that is 28 were predicted to be diabetic, and those 28 were part of the actually diabetic. That's what it means. What does this 10 mean? This 10 means this 10 were predicted to be diabetic, but they were actually not diabetic, they were healthy. This 19 means they were actually predicted to be they were actually predicted to be not diabetic, but they were actually diabetic. Okay, so if you are confused, let me show you the exact documentation of confusion matrix. Here it is. So here, read it. Definition: a confusion matrix C is the Cij is equal to number of observation to be in group I. Okay, so now group I predicted to be in group J. Simple, very simple. You just need to read it like this way. Okay, 10. So you have to come from the middle. Okay, so 10 values are predicted to be 1, but they were actually in 0. So these two guys are bad, if you will. Okay, these two guys are bad. You don't want that. You want the values to be here because this value represents 0. This value represents 97 0 predictions are made, and they are 97 are part of this 0 class. That's what it represents, right? And what does it represent? 28 predictions were made that they were diabetic, and they were actually diabetic. So we want this thing. Okay, and accuracy score is basically these two divided by entire sum of this. Okay, that's accuracy score. This 0.81. So logistic regression is performed very well. Now this is what we call a classification report. Now sometimes what happens is this accuracy is not enough, because let's say what happens is if this guy dominates, if this guy is very high, data is imbalanced, then it creates problem. For example, let's say this was some 1 million and this was 0. This was 1 and this was 0. And still the accuracy would be pretty high, right? You are getting why I'm saying that. because one will always dominate in the accuracy part, and we don't want that. The one values were predicted very badly, right? If this was 0. So that's why we use some other matrix. That's why I have also used one more function here. If you observe, I didn't mention earlier for some intentionally, I use this classification report function. Now, what does this do is it generates some more performance metrics. So I'm not going to go into all of these, but these three are important: precision, recall, and FN score. Now, what does this precision, recall, FN score mean? They help us actually see that accuracy is not lying to us, because accuracy can lie to you at times. At the very general sense, even if you don't know what does this mean, you can see that the precision for a precision, recall, and FN score for 0 is pretty high. And it should not surprise you, because the wrong 0 values are pretty less, right? So out of all the 0 predictions, only 19 were wrong, 97 were right. So it should make sense why these are so great. I'll come to the formula in a bit, but it should make sense why these values are great. But once precision, recall, and FN score are bad, because you can say out of all one predictions, the ratio is not that much significantly different. Okay, the 28 and 10, they are not that much different. That's why it's not too bad, but it's not as good as this 0. Okay, so now coming to the formal definition of precision is precision for a particular class. For example, a precision for class 0, or maybe let me just talk with this class 1. Class 1, or maybe a precision for a person being diabetic is, that is, out of all the predicted values for that class, how many of them were true? Now, let me repeat myself again. Let me just open my Python shell so that I can show you the calculation. Now, what is the precision for a class? Out of total predicted values for that class. For 1, total predicted values were what? 28 plus 10, right? How many of those were correct? 28 were correct, right? So 28 divided by 28 plus 10, 38. And that's what this is, 0.736, or of course it is rounded to 74. That's precision. Out of total, I'm repeating, when you hear the term precision, you should talk about the predicted value. Of the total predicted values for that class, how many of them were true? Right? So is that true? 38 values were predicted, out of 28 were true. So that's precision. You can of course see for 0 also. Precision for 0 is, out of total predicted values for 0, how many were the true? So it seems like 97 out of 97 plus 10 values was true. Let's explain why this is. Okay, it is 19, right? Sorry, it's 19. That will explain why it's 0.84. Right? So precision basically deals with the number of predictions. So precision for a class is basically number of predictions for that class. Out of number of predictions for that class, how many of them were true? That's the idea. Okay, so it gives a better sense of if a class was predicted well or not, right? You can already say that out of all the predictions of 1, only 28 were right. So it definitely reduces the accuracy score. Accuracy was 80, but you can see that 1 was not predicted well. Now let's talk about recall. Now when you talk about recall, you basically consider the ground truth. You have to always think about the ground truth. That is, recall for a particular class, for example, let's just say for 1, is out of total truth values of 1, how many were correctly predicted? Right, that's the idea. Recall, for recall, you have to think about the base truth. Baseline is your truth. So out of total actual truths, that is 29 plus 18, how many of those were correctly predicted? Okay, so what I mean is 28 out of 19 plus 28 ground truths were correctly predicted. That explains why this is 0.60. Right, let's just calculate for 0 then. Out of total actual truth values, how many of them were correctly predicted? So 97 out of 107, 97 plus 10 were correctly predicted. 97 out of 107 ground truths were correctly predicted. So it explains why it's 0.91. Now what is this FN score is? FN score is basically the harmonic mean of precision and recall. It also gives a better sense of how well that value is predicted. So you know harmonic mean, right? It is It is basically 2 into P into R upon P plus R. That's a harmonic. So that's the idea. Whenever you talk about precision, you have to look about the predicted values. Okay, so precision for 1 will be out of total 1's prediction, how many of the correct? To talk about 1's recall, you have to talk about how actual truths. Out of actual truth values of 1, how many are correct? That's the idea. And F1 score is harmonic mean. It also gives you a relative measure of how well that value is predicted. You can clearly see class 1 was not predicted well and class 8 is predicted very well. And it's not happening like without any reason. There's a reason why this happens. This happens because we already see in explore data analysis that the values of zeros that a person was healthy was more. So the model got to learn more of zeros data. The person got to learn more about what are the characteristics of a person not being diabetic. That's the reason. We have more values for non-diabetic persons. That is the reason we are getting high accuracy, high performance for prediction of zeros. All right. So there are some other metrics also, but that they are not much important. But these three are very good. Okay, generally accuracy works, but sometimes you might have to see these three also. All right. So let's move on to next algorithm, KNN. Now, KNN is a very simple algorithm. it is algorithm elementary school student can also understand. The way it works is whenever given a sample point, what we do is we compare its nearest neighbors, k nearest neighbors, based on the Euclidean distance. Now, what is the Euclidean distance? You know that between 2 points x1, x2, and x1, y1, and x2, y2, the Euclidean distance is square root of y1 minus y2 whole square plus x2 minus x1 whole square. That is the Euclidean distance. We calculate the Euclidean distances. Based on Euclidean distance, we identify the nearest neighbors, and we classify that. We classify the input based on the most voted category in its neighbor. Very simple. Okay, for a given input x, the new input, we actually examine its neighborhood, and depending on what majority vote is get to category, we are going to classify. That's the k nearest neighbor, and it performed decently. It's not better than logistic regression. The 76% accuracy and precision recall is very obvious. The precision recall reference score of 0 is better and should not come as a surprise. And 1 was not predicted very well. You can see that. Although if you observe here, the recall of 1 is better here than logistic regression. Right. Sort of actual values, 1 is getting betterly predicted by KNN here. So this is something that you can play around with it. Then comes linear SVM. Now, support vector machines. They are very famous algorithms. The way a support vector machine works is it has a name, support vectors in it. Now, what are support vectors? When we create a decision boundary, the point closest to the decision boundary are what you call support vectors. The decision boundary of support vector machine, the point closest to the decision boundary are what you call support vectors. And support vector machine aims at increasing the distance between the decision boundary and those support vectors. The image will make things more clearer. So it is what you call a maximum. We try to maximize the margin. What is the margin? It's the distance between the decision boundary and the threshold. Okay, so those thresholds are basically called support vectors because they kind of support the decision boundary. Okay, that's the idea behind it. And we try to maximize this margin so that we can get a better fit. And it seems like support vector machines also kind of similar to logistic regression, but again, not that much difference with the score and all. Then there is a kernel sphere. Now it might happen. I told you right. Sometimes data might not be linearly separable. Better to say the linear decision boundary might not work. So a data might not be linear separable, but we don't have any way. The decision boundary is a hyperplane. It's a hyperplane, and it needs somewhat kind of a linearly separable data set. Then it can work. Now, the idea behind kernel support vector machine, this is called the kernel trick. They both are same only. Okay, it's just called it kernel SVM because we are using some non-linear kernel. When I use a linear kernel, I basically mean I'm just trying to fit that line or hyperplane, if you will. But in kernel SVM, what I do is when the data is not linearly separable, we map the data to some higher dimension, and now the data becomes linearly separable. Now, the kernel is basically that function which maps the data to some higher dimension. Okay, and let's see how kernel SVMs work. Kernel SVM also didn't do very well. They are also 77. It was okay, right? Here are the classification report. Then there is this naive bias. Naive bias works on the famous Bayes algorithm. Uh, it is naive bias. Generally, people talk about multinomial naive bias, but Sklearn implements it with a Gaussian naive bias. Now, what is a Gaussian naive bias? Basically, what you do is you create Gaussian distributions of every feature for a given category. For example, for insulin, we'll create insulin feature. We'll get two Gaussian distribution, one for diabetic patients and one for non-diabetic patients. Okay, we create Gaussian distributions. And then for every feature we do this, right? For glucose also we'll do this. For glucose we'll create one Gaussian, create a Gaussian distribution for diabetic and one for non-diabetic. And then when a new value is provided, we calculate using this formula. We calculate the score for a particular category. Okay, for probability of y equals to y, we calculate the score. Okay, and depending on which category gets the highest score, we assign the category to it. This probability of y is the posterior probability. Now, how do you get the posterior probability? Basically, for p of y equals to 0, you count all the non-diabetic patients and divide by total number of patients. For diabetic patients, you count all the diabetic patients and divide by total number of patients. How do you calculate those things? Probability of xi when y. These are basically, they are not called probabilities, they are basically called likelihoods. There's some mathematical jargon there because probabilities in terms of some continuous functions that we are using here, it is generally area under the curve. So we call it likelihood. Okay, that's just a mathematical jargon. Don't stress on it too much. So we calculate those with the help of the scary looking formula of Gaussian distribution. And depending on which of the category gets the highest score, we assign it to that. And naive bias also performs okay. So we have seen that majority of the algorithms has efficiency greater than 75%. And logistic regression has a very good accuracy of 81, above 81%. And of course, the confusion matrix also looks kind of similar, not much difference. Now, decision trees. Now, these are the most simplest kind of algorithms. They work on simple decision rules. For example, what it will do is it will create a decision tree. In the sense, at the root, let's just say there is your insulin greater than some point. If it is not, then let's just say we go into one side if insulin is not greater than something. And that's why we'll check if glucose is greater than some threshold. If it is that, then you have a diabetes. That's you know. So that is the idea of decision tree, and we don't make this separations and anywho. There's a criteria. Generally, it's called the entropy. That is basically we check if we are able to reduce the randomness. We are able to reduce the randomness between the data points we are making this split. That's the idea of this entropy. There is one more metric, Gini used, but both works. It depends. I tested with Gini also, but entropy works better. That's why I use entropy. Entropy is just a measure of randomness. You might be knowing this. And it actually performed poorly, to be honest. It is predicting worst, right? Now the random forest and XGBoost. Now random forest and XGBoost are basically decision trees on steroids. Now what happens is decision trees are very old models. They have been there for I guess 1960s. They're very old models. And they were about to die, but then came this random forest. Now I don't know how much you are familiar with this, but random forest is a very famous algorithm. It is used by Microsoft in one of its games. So it is used to detect your basically hand movements or something like that. Random forest is a very powerful algorithm. Now the way random forest works is it is also called an ensemble technique. Now what's called ensemble? Ensemble stands for group, right? So what it does, it creates many decision trees. Okay, maybe I've provided here 100, so it creates 100 decision trees by taking random inputs. Okay, so we have here I guess 500 or so inputs. So it takes, let's just say first it takes 200, then it takes some 300. It decides how many it has to take. There's some randomness involved in making decision trees. And whenever I give it a new input, it evaluates every decision tree on this input. And in case of classification, it returns the most voted category. That is maximum votes that it gets from all these decision trees. That's what is returned. That's how random forest works. And then XGBoost. Now XGBoost is what the XG stands for extreme gradient boosting. Now the idea of gradient boosting is to build sequence of decision trees. But if I discuss XGBoost in this video, it will be very large. So you can just consider it as a decision tree on steroids. It is a very computational heavy algorithm, but it is a very good algorithm. By the way, you can already see the random forest, and XGBoost gives a very good accuracy of nearly 80, right? So, and it seems like one's predictions have also improved. You can see that the precision recall of one is more, of course, not random forest, but XGBoost is able to perform well in case of one, right? Let me just see what was the way, how logistic regression worked. 0.74, 0.60, 0.66, and how did XGBoost work? Yeah, it also performed okay. Its recall was high, so it was able to actually maintain the relevance of original values, right? So the ground truths were you can already see the predicted ones were very good here. That's good. And last but not least, multi-layer perceptron classifier. Now this is actually a deep learning model. It is multi-layer perceptron is basically a neural network, which is used for binary classification. Now what is a neural network? Neural network is basically a limited imitation of how our brain works. Now here you can see a simple neural network. A perceptron is a very simple kind of neural network used for binary classification. The way it works is we have some input nodes and they are given to some what you call hidden layers, and there some calculation happens and we get some output. The output is binary, so we only have one node at the output layer, if you will. Now how do you think this works? It works by taking the input and some calculations happen here, or technically activations happen here, and depending on this edges, these edges are also called synapses, and depending on this way these activations work. And again we can see a multi-layer perceptron classifier. It's also okay, it didn't perform that well. So we have seen a lot of machine learning algorithms. Now let's just compare all of them. Now it seems like logistic regression is the winner. It has the highest accuracy score, and then random forest, then XGBoost, and so on, right? Then SVM and so on. But we should not end this thing here. Okay, you might think that okay, logistic regression gives highest accuracy. Okay, that's great. I'll use regression. But who knows the split favored logistic regression? The training and test split that we made favored logistic regression. The way logistic regression learns. We cannot be sure. So we have to do something what we call KFold cross validation. Now, what is KFold cross validation is? We divide our training set into K parts. That's what this K stands for. KFold is just a fancy name for a part. Okay, don't worry about it. We divide into K parts. Then what we do is we take every part. Let's just say we divide the training set into 10 parts. And we take every part as a testing set, and remaining 9 parts is a training set, and we build the model again. And calculate the accuracy there. Make sense? We calculate the accuracies of, basically we are calculating the accuracies of k different, we are basing the accuracy of our model for k different splits, right? We are training 10 models. So this gives me a better understanding of how well my model is performing. Okay, so that's why I've created this function. It takes my classifier, it takes the training set, and what it does is this cross-value score function of scikit-learn takes my classifier, takes my training set, and performs it with K-fold cross validation, and returns me all the scores of different classifiers trained. So it will return me if I have K's value is 10. Generally, this CV represents number of folds. So it will return 10 accuracies of 10 different models trained. So basically, it will, if I want to give an example, it will train 10 different kernel SVMs and basically return me the scores of each and every SVM. And then I calculate the mean score, and I'm also calculating the standard deviation because I want to see if the mean of this that how well is the model performing. Is it so the case that for one time it's performing something like 90%, which is causing its mean to increase, and some values are very less. So I want to see how spread the values of averages are. That's why I'm calculating the standard score. So that's what this function does. The fancy function are written to make my life easy again. So let's just calculate the mean accuracy for everyone. So I've calculated, and let me just show you the result what I got. So here's the result, and it seems like every one of our no algorithm was able to clear that 80% mark. And logistic regression still is in the race, but MLP classifier seems like to overtake him. But still we can see that the standard deviation of nearly 6% for 5 or 6% of both of them. So it means the values are lie between 75 plus minus 6, something like that. Okay. So yeah, I guess it's still very bad accuracy. We can definitely improve it by maybe eliminating some features, or maybe using TensorFlow or something like that. You can use some artificial neural networks and try. But definitely this can be improved. This is definitely not acceptable, 75%, but they've come a long way. These are some most famous algorithms that I tried this, and there was a lot of learning involved here. And I hope you got something out of the video. I know I didn't explain them into detail, but I hope you got a sense of how various classification algorithms. And once again, this code will be uploaded on my Kaggle, so feel free to check that out. And thank you for watching. Leave a like if you found it was a helpful video.